So tutorial 6. So the first question for tutorial 6 is actually, given that A stable 555 timer has the following external components. They say R1 equals to 100 kilo ohms, R2 equals to 47 kilo ohms, C1 equals to 10 microfarad. What is the mark and space? So what is the mark and space? So what is mark and space? Basically, mark and space is saying that how much time is on, how much time is off. Mark is on, space is off. So what we are trying to do is find how much time it was on the output, how much time it was off the output. The only information we are given, R1 is 100K, R2 is 47K, C1 is 10 microfarad. So how do we calculate that? The only two formulas that were given that day was frequency and duty cycle. Okay, so how do we use these two information? Because now, for the R1, R2, and C1, this one actually refers back to the image in the lecture slides. Okay. You can see here. It's actually referring to this image. So your R1 is value here, R2 value here, the C external value. So when they mention the R1, R2, and C is referring to this image. Okay, so this is your 5 timer. So they're saying that at the output, how much time it was on, mark, how much time it was off, space. So, and the only formula we have is these two formulas, which is the frequency of the oscillation and percentage of duty cycle. So how would we use this information to determine the time? So, okay, first thing, what is frequency? Frequency means what? Meaning that if you got an output, how many cycles in 1 second, correct? Frequency is how many cycles in 1 second. So 1 over frequency, which is time, is basically the time, right? So 1 over frequency, you get the time of 1 cycle. So far, okay, right? So when we are talking about frequency, what we mean by frequency? How many cycles in 1 second? And then if 1 over frequency, let's say is t, time will be the time for 1 cycle. So then how do I know how much time is for mark, how much time is for space? This is when duty cycle comes in. So what does it mean by duty cycle? Duty cycle actually means this. Because usually your time is, your output signal doesn't mean must be half on, half off. It could be half on, a bit like that. That means it was on longer, off shorter like that. So this was 1 cycle. So a duty cycle actually indicates how many percentage of on time. Okay? So when this duty cycle times 100%, what I mean by let's say it's 75%. So if you got duty cycle equals to 75%, that means 75% was on, 25% was off. So that's actually what it meant by duty cycle. So knowing these two data, how would I calculate how much time was marked, how much time was missed? Anyone? Online? Offline? Just using these two information, how would I know how much time was on, how much time was off? What should I do? Okay, substitute in R1, R2 to calculate what value first? Okay, let's say I calculate my duty cycle first. Okay. So let's say I calculate my duty cycle equals to R1 was how much? You read out for me. 100 K plus 47 K over 100 K plus 2 times 47 K times 100%. So what do I get? 75.8%. Okay, so what does 75.8% mean? That means it was on for 75.8% and off for 20+%. Okay, 75% was on, 75.8% off, and 20-something was off. Okay, so I know the percentage is on, I know the percentage is off. What else do I need to know? I need to know what is the time for one cycle, correct? So how do I find the time for one cycle? Okay, so that means now I find the frequency. So 1.44 over R1 is 100K plus 2 times R2 is 47 and 3 times the capacitance value was 1096. So that will be how much? .7423 hertz, is it? Sure, 1.44 divided by 100K plus 2 times 47K times 10 times 5, 96. Right? Is this? Sure. Sure. Okay. So that means the time, one time period will be how much? 1 over frequency, correct? So that means how much seconds? 1.35 seconds. So that means one time period is 1.35 seconds. Meaning the mark will be how much seconds? Correct. So first you got the time period is 1.35 seconds. Therefore, you know that your mark equals to 75.8% of 1.35 seconds. And 1.35, you get how much? What's the answer? Around 75.8% of 1.35 seconds, you get how many seconds? Yeah, around 1 second. Space equals to, you can just take 1.35 minus 1 is 0.35 seconds. Okay. So that is one way to calculate it using the two formulas that you can use for your 555 time. Okay. Offline, okay. Online, okay. Any questions from online? No. Okay. Okay, then shall we move on to the next question? You need time? Can move on? Okay. Okay. What does the second question ask? Second question asks, using a 500 picofarad capacitor, design the A-stable circuit in the figure below to obtain a square wave with a 65 kilohertz frequency and 80% duty cycle. specify the values of RA and RB. So basically, find the values of R1 and R2 given those values. So we got two equations, two unknowns. Should be no problem. This one is just normal maths, right? Did anyone do the calculations? Because this one is because they already give you the duty cycle, they already give you the frequency. Basically, find the value of R1 and R2. So we just substitute in the values. Frequency, they said it needs to be 65 kilohertz. So 65 kilohertz equals to 1.44. Divide R1 plus 2R2 times capacitance is 500 pico. So 500 times 10 negative 12. That is one equation. Then you can simplify it. R1 plus 2R2 4 over 500 times 10 negative 12 and 65 times 10. Okay. So but R2 equals to this value. What's the second value you need? You need the duty cycle. It needs to be 80%. So in our words, 0.8 equals to R1 plus R2 over R1 plus 2 R2. Okay. Times up 0.8 R1 plus 1.6 R2 equals to R1 plus R2. 1.6 minus 0.6 R2 equals to 0.2 R1. Means R1 equals to 3. Good? 2 to 4, 6. Yeah. So then substitute this into here to get either R1 or R2. Substitute R1 inside here to get R2, then you get the R2 value, and then after that you get the R1 value. So did anyone calculate the value of R1 and R2? Online people? Did someone from online give me the value of R1 and R2? Okay, R1 is 26.6. Okay, R2, 8.6. Okay, correct. So R1 equals yeah, very good. Got two calculations. So this one is rather straightforward. We just use the formula we substitute. Okay, no problems here, no problems online. Then we go on to question 3. Now, question 3. see here is that referring to the figure below, a motor is connected to the 555 timer. Basically, the motor was connected to the output. Okay. So previously we see the output is always either high or low or high or low. Now we are connected to a motor. So basically when it's high, it's on, low is off. So now when they say when R1 equals to 1K, R2 equals to 3K, what would be the duty cycle at pin 3, and then after that you swap it. R1 equals to 3K, R2 equals to 1K. You calculate what's the duty cycle. So first step is to calculate the duty cycle first. Then after that, try to figure out what does the answer represent. Okay, so calculating the duty cycle should be fine, just using the formula. So what duty cycle you get for part A and what duty cycle do you get for part B? So, okay, online say part A is 57.14, part B is 80%. Okay, correct. So part A is 57%, part B is 80%. So you found the duty cycle. So now, based on the answer that you get, which one of the scenario A, B will cause the motor to spin faster and why? So which one do you think will make it spin faster? B. Why B? Okay, so 80% means what? Correct. So what happened to the motor? So what happened to the motor when it's high? It's spinning. Then when it's low, okay, then it spins again and stops. But in general, what we see is just B. So because it's like spin 80% of the time, so supposedly stop 20% of the time. Spin, stop, spin, stop. So basically, it's actually spinning faster. Compared to the other one is spin and stop longer. So it's sort of slow down. So in general, it's like in average like that. So if you spin more time, then stop it. Spin more time, stop it. It's like you go, stop, go, stop, go, stop, go, stop. So in average, it seems to be running faster compared to the other one where it's stop longer. Okay. So that's the, when you look at the duty cycle, then you should be able to tell whether which one is spinning. Because this one is on longer. 80% is on longer. Therefore, that means you are spinning over the cycle. So as long as you understand what the duty cycle means, which means the percentage of on time, then it's really well. Okay. So the keyword today is duty cycle. What it means? It means on time. Okay. And the last question. Now, based on the figure below, briefly explain why the duty cycle of the basic timer A stable multivibrator is always more than 50%. They say in this case, your duty cycle will always be more than 50%. Why? Why can you make that assumption, or why can he make this statement that the duty cycle will always be more than 50%? Based on what? This one is based on, you must know how your A-stable multivibrator works. So looking at how it works, why can you make that assumption or make that statement that it is always more than 50%? Basically, they said it's always on more than 50%. Basically, it's more on than off. Why? So the clue is to look at the how it works. anyone has any suggestion of, because this is how your stable multivibrator runs, right? So based on what can you claim that it will always be more than 50 cycles? Why do you say it's always on longer compared to off? Anyone from online wants to share? Okay, no answer from online.
Hello.
Okay, now looking at this thing here, when is this thing on? When is the output on? When is it on? Sorry? What? Upper and lower zero. What is upper comparator and lower comparator? Is it when both are zero is no change? So basically you want the Q to be 1. No, 1. You need the Q to be 1. Because it comes in here, because you see the not here, right? Then it goes 0, but then not again go back 1. Yeah. So you need the Q to be 1. So when is Q1? When is Q set? When is it set? When S is 1, R is 0, correct? When is S is 1, R is 0? When happens? Your lower comparator is high. When is your lower comparator high? Are you sure 2 or 3? Now, okay, look at these two comparators, upper comparator and lower comparator. So, okay, when we see comparator, right, how we know whether the output is high or low? You always take the value at the non-inverting leg minus the value at the inverting leg. So as long as the value at the non-inverting leg is higher than the value at the inverting leg, the output is high. Once your value from the non-inverting leg is lower than the value at the inverting leg, your output becomes low. Correct? Okay. So now, if you look at both of your comparator, right, there are two inputs, correct? This input and this input is dependent on the voltage across the external capacitor. Right? And then this input and this input is connected to this line. So what we said yesterday, this line is a VCC line. Okay? So and we got 3 resistors inside the VCC line. Okay? From between VCC to ground, we got 3 resistors with the same value. That means the voltage across it, they're split equally. So that means voltage across here, this RC, from here to here, is 1/3 VCC. Voltage from here to here is 2/3 VCC. Voltage from above to here is 3/3 VCC. So that means the threshold here is what? 1/3 VCC. Or the value from here to here is 2/3 VCC. So you look at this lower comparator, 1/3 VCC. At first, this one is voltage across your capacitor. Initially, they said capacitor was not charged, is 0. So 1/3 VCC obviously bigger than 0. So your output is high at the moment. Okay. Well, this one is 0 minus 1/3. So output is low. So R low as high, that means Q will be 1. So that means the output will be high. Okay? And then, because it's not here, that means it's low. Low here, that means transistor off at the moment. So no discharge. So they only start charging your capacitor. So charge until what happens? Now, when this thing starts to hit 1/3 VCC and go higher, what happens? Now, this one becomes low. Output becomes low because your output here is only 1/3 VCC. So this value equals 0. Then it goes bigger. Once it goes above 1/3 VCC, your output here equals was high. Now it's a low output. But it's still less than 2/3 VCC, so that means this one still maintained as low. So both low, that means no change. So output still maintained as high, transistor still off. Right? Charge on some more until voltage across here becomes 2/3 VCC. This one still low, but now here, what happens? My input here now is 2/3 VCC. I'm trying to go higher. Or here is 2/3 VCC. So that means at first your output is negative, now becomes a high output because this one go above 2/3 VCC. Or this one is stuck at 2/3 VCC. So now because this one goes high, this one low, what happens? Reset. So that means 0, that means your output now goes low. Or here that means high. High here means you on your transistor. Transistor on now, so that means you can start to discharge. So and then when you discharge, what happens? You discharge, then the voltage across here starts to drop. Okay, the voltage across the external capacitor starts to drop. What happens? Then the voltage starts to drop. So at first this one go high, that means it becomes high. Drop, that means now here is low. Here will still maintain low. So low and low, still no change. That means your output is still low. Transistor still on, you still continue discharging. Discharge until it hits 1/3 VCC. So this is low, right? Now when it goes below 1/3 VCC, now this one goes high. Once it goes high, what happens? That means now it goes set. That means the output will be high. Which brings this to low, which means you off the capacitor, which means you don't discharge through this area. So no discharge, then you start charging back. So that's how the multivibrator works. So on time is when this thing is charging, the external capacitor is charging. Off time is when you are discharging. Right? So how long does it take to on? And how long it takes off? That means on time is charging this capacitor, and you're charging this capacitor through R1 and R2. But then discharging, which is the off time, you discharge across that R2 only. Okay? So the key point here is that when you're charging across R1 and R2, while you're discharging, you're only charging across R2. So now, do you still remember for capacitor, how is your charging time related to the resistance plus capacitance value? Remember something for time constant? How equals to RC? Something that sounds like that. Right? So the charging, how long it takes to charge or discharge is related to something called the time constant, RC. I mean, RC does not equal to 100% charge. I think RC you only get around 63%. That means one time constant, it charges up until 63%. Then they will say that usually after 5 time constant, you're almost charging 100%. So same thing is going to discharge. So let's say to charge up to 63%, R times C, to discharge to discharge 63%, so R times C. So one R value is R1 plus R2, or the other R value is only R2. So charging time longer or discharging time longer? You take longer to charge, correct? Compared to discharge. So you take longer to charge, that means the on time is longer, correct? Because your on time is when the capacitor was charging. The off time was when your capacitor was discharging, correct? So that is why you can say that the duty cycle will be always more than 50%. Because it took longer to charge compared to discharge. So that's the reason why you can say that the duty cycle is more than 50%. Yeah, is that clear? Online people, okay? Yep. Okay. Good. So that is it for question 4. Now, before we leave, let's ask you one more question. Okay, since we are so way ahead of time. Okay, looking at this, this is when we said that you need to charge, discharge depending on 1/3 VCC and 2/3 VCC. Correct? Then remember, we went further on and say that when we put in a control voltage. Okay? So now if I put in a control voltage, it goes from half control and one control. So just now was 1/3 VCC here, 2/3 VCC, right? It went up and down. Now why is it now when I put a control voltage, you end up with control, V control and half V control? Why is it half V control? And the only difference is that I put in a control voltage at where? I put in a control voltage at here, which is at pin 5. Where is pin 5 is here. Yeah. So previously, your upper comparator was linked to 2/3 VCC here and 1/3 VCC here, right? So now by putting in the voltage across here, what happens? So I put in a voltage here, so the control voltage is at pin 5 here. So why by just putting a control voltage at pin 5 there, now it's the control voltage controlling it, and it's V control and half V control. Sorry? No, okay. V control, okay, so at first, the upper one was 2/3 VCC, right? So 2/3 VCC, because here was 2/3 VCC. Now I changed it already. So now the upper one V control, okay, that one quite clear. But why the other one is half V control? Why half V control? Why not 1/3 VCC? Like this one, I change this to V control already because I'm affecting my upper comparator. But what happened to my lower comparator? Why the bottom part was not 1/3 VCC? Why did I end up being V control? Half V control, not even V control. Right? Uh-huh. Correct? Yep. Correct. So basically when you connect here, you like bypass that part. So that means from here to here is V control, and there's only 2 resistors, and both resistance value are the same. The second point is under the first resistor. So it's halfway point. So that's why it's the other value to control the lower comparator is half of your V control. Correct. That's the last step. Okay. So when you put V control, you bypass here. So that means now under your V control, you've got 2 resistors. Because the resistors value are the same. So at this point is V control, the lower value to control the the value to control the lower comparator is the value after the resistor, which is half V control. Because this is the other half of it. Okay? Okay. That's it. Any questions? Any questions online?